Welcome to the unit on equations and inequalities. Review exercises. The objectives for this session are to review previous topics through exercises, namely, specify the elements of a set, simplify numeric expressions, and label key points of a quadratic on a graph. On the screen you have the first two review exercises. Pause the video and have a go. Press play when you're ready to go on to the third exercise. And here's the third exercise. Pause the video and have a go. Press play when you're ready to view the solutions. Let's now have a go at review exercise 1A. We have that the set A consists of the elements 1, 2, 3, 4, 8 and 12. We have that the set B consists of the factors of 20, excluding 20, and the universal set consists of the elements of the natural numbers x such that x is less than or equal to 15. We are required to write down the members of A intersect B. So let's solve this. So we have the set A as shown. B, the factors of 20, is equal to the set of numbers 1, 2, 4, 5 and 10. The universal set, which consists of the natural numbers x such that x is less than or equal to 15. So the universal set is the set of whole numbers from 1 to 15 inclusive. We are required to write down the members of A intersect B, or A and B. Let's begin by producing a Venn diagram to help us. So let's start with what's common to both sets, A and B. The number 1, the number 2, and the number 4. Nothing else seems to be common. And now for exercise 1B. We're required to find A union B complement, which means everything not in A or B. So let's find what's in A. We've already covered 1, 2, 4, which is in A. So the rest of the elements are 3, 8 and 12. So we put those in A, but not in A intersect B. We now consider set B. The elements 1, 2 and 4 are in set B and A, and we've already considered those, and only 5 and 10 are left. So we add those to the set B as well, but they're not in A. So what's left? What's in the universal set which is not in A or B? We remove 1, 2, 3, 4, 5, 8, 10 and 12. So these have all been already taken account of. And what's left is 6, 7, 9, 11, 13, 14 and 15. And so the set of numbers A union B complement is equal to 6, 7, 9, 11, 13, 14 and 15 as shown. Now for review exercise 2A. We are required to simplify square root of 288. So let's solve this. 288 is 2 times 144. We're going to break this down into all its prime factors. 144 is 2 times 72. 72 is 8 times 9. 8 is 2 cubed, and 9 is 3 squared. And then we can simplify a little further. We've added the indices, so we have 2 to the power 5 here, and we leave 3 squared as it is. So if we're square rooting this, we have to square root 2 to the 5 times 3 squared. Or square root of 2 times 2 to the 4 times 3 squared, because it's easier to square root some of these numbers in this format. So root 2 stays as it is. 2 to the 4th square rooted breaks down into 2 times 2. And square root of 3 squared is equal to 3. So we're left with 12 root 2, as shown. Now for exercise 2b, we're required to simplify the expression on your screen. So let's try simplifying this. We're going to begin by looking at the numbers in the square roots and express them as their prime factors. So root 18 becomes root 2 times 9. Root 50 becomes root 2 times 25. The expressions in the square roots need to be broken down further, but we'll do that in the next line. We leave 5, 3 and 15 as they are. And then we break down further. So 2 times 9 becomes 2 times 3 squared. And 2 times 25 becomes 2 times 5 squared. And of course 5, 3 and 15 remain as they are. Now we can start to get rid of some numbers. So let's split this first. Root of 2 times 3 squared becomes root 2 times root 3 squared. Root 2 times 5 squared becomes root 2 times root 5 squared. And 5, 3 and 15 again stay as they are. Root 3 squared becomes 3. And root 5 squared becomes 5. Now we can tidy up. So 5 times 3 becomes 15. Root 2 stays as it is. 3 times 5 becomes 15. And root 2 again stays as it is here. And 15 remains as it is also. So we have 15 root 2 over 15 is root 2. And similarly for the second term, to give us 2 root 2, as shown. Now let's solve review exercise 3. We are required to match the equations to the correct graph and label the points of intersection with the axes as well as the coordinates of the turning point. So how do we match the equations to the graphs? Let's try solving this. Now, equation of part 3a is the only equation with a negative a coefficient. So the quadratic must be upside down. The only function that does this is the second graph. Now the equation in part 3c is the only equation which is entirely positive, because x minus 3 all squared is greater than or equal to 0, and 5 is greater than 0, so it does not cross the x-axis at all. And so we've matched the third diagram to equation C. And so that leaves us with the remaining graph, which is B. So that has to be the first one, although there are more mathematical ways of finding this out as well. So let's now look at each graph and label the points. Now the intersection with the x-axis of the curve y equals 16 minus x squared is found when y equals 0. So when y equals 0, 16 minus x squared equals 0, or 16 equals x squared, as shown. In other words, x is equal to plus or minus 4. So we have 4, 0 and minus 4, 0 as 2 points of intersection with the x-axis. And now for the intersection with the y-axis. This is when x equals 0. Now when x equals 0, y is equal to 16. We're simply plugging this in to our equation. And so the point of intersection with the y-axis is 0, 16. What about the turning point? When 16 minus x squared is largest, that's when the turning point occurs, i.e. when x squared is smallest, because notice x squared is positive and we are taking that away from 16. What is the smallest value a positive number could take? Clearly it's x equals 0, and when x equals 0, y equals 16. Hence the turning point is at 0, 16. Now let's have a go at review exercise 3b. Let's find the intersections with the x-axis. So when y equals 0, let's find x. So when y equals 0, 3x minus 2 times x minus 5 equals 0 also. Therefore, x equals 2 over 3, or x equals 5. And so our points of intersection are 2/3 0 and 5, 0. What about the intersection with the y-axis? This occurs when x equals 0. So we plug x equals 0 into the equation to give us 0 minus 2 times 0 minus 5. And tidying up gives us that y equals 10. So the point of intersection with the y-axis is 0, 10. So what about the turning point? This occurs when x is halfway between 5 and 2/3. In other words, when x is at 2 and 5/6. And therefore plugging in x equals 2 and 5/6 into the equation, we have that y is equal to 14 and a 12th. So the turning point is at 2 and 5/6, 14 and a 12th, as shown. And finally for exercise 3c. There is no intersection with the x-axis since y is positive. Let's have a look at the intersection with the y-axis. When x equals 0, what is y? We simply plug in x equals 0 into our equation to give us y equals 14 here. And finally our turning point. This occurs when x minus 3 all squared plus 5 is smallest. In other words, when x is equal to 3. because that makes the expression x minus 3 all squared equal to 0. And we can't get anything smaller than that. Therefore, the turning point is at 3, 5, as shown. This brings us to the end of this session. If you have understood its contents, you should be able to specify the elements of a set, simplify numeric expressions, and label key points of a quadratic on a graph. Thank you very much for listening.